Hello, this is Akhil Chandel, and in this video, I will be presenting an analysis and a critique for the academic paper titled Distributed Self-Monitoring Sensor Networks via Markov Switching Dynamic Linear Models. The paper was written by Fang, Juan, and Simon Dobson, all from the School of Computer Science, University of St. Andrews, United Kingdom. It was presented at 13th International Conference on Self-Adaptive and Self-Organizing Systems SASO in the year 2019. In brief, the paper talks about wireless sensor networks and the limitations and challenges that are faced by the sensors and the error that contaminates the sensor readings. The authors then go on to propose an efficient self monitoring, self managing, and self adaptive sensing framework based on a dynamic hybrid Bayesian network that combines the hidden Markov model and dynamic linear model. Finally, they evaluate their framework using both synthetically generated data and real sensor data. The problem statement is defined at the very beginning in a clear and precise manner. As the paper deals with wireless sensor networks, it tries to take into account the most critical challenge in a WSN, which is sensor errors. By definition, a sensor error is a reading which is a deviation from the normal patterns exhibited by true readings. These errors can be attributed to hardware conditions and adversarial external factors such as high variance in temperature and humidity. Hardware conditions like malfunctions, low battery, and connection failure all can contribute to erroneous readings. Sensor errors can degrade the performance of a wireless sensor network, affect its monitoring performance, and result in loss of information fidelity and wrong decision making. As wireless sensor network relies heavily on sensor readings, an error in the sensor data can render the system being unreliable along with the unexpected behavior of the system. These are the problems which this paper tries to solve. With the proposed solution, the authors aim to make sure that the data collected from the sensors is trustworthy representation of the physical process. As can be seen in the paper as well, the authors term sensor error as the most critical challenge in a wireless sensor network. A wireless sensor network, by definition, is a group of spatially dispersed and dedicated sensors, and these sensors have various constraints due to nature of them being wireless and small in size. These constraints range from power consumption constraints, resilience, that is the ability to cope with node failures, deployment constraints, to resistance to damage from extreme conditions. With these constraints, it is tough for the sensors to be fully resistant to errors. Even though there has been many researches and studies done towards this field, there is a scope for a lot of improvement, partly because of WSNs becoming more complex and most of these studies not being implemented in real life WSN. Thus, this problem is still a big challenge. Moving on to studies in a similar area with similar motives, the paper even talks about related works. Many have looked into automatic detection and management of sensor errors. A common approach towards this direction is using the values from the neighboring sensors. These values can be used to predict the ground truth values, which in turn can help in detecting and measuring sensor error by exploring spatial and temporal correlations. There has been a solution which employs a semi blind approach to calibrate sensors with the aid of infrequent true readings from high fidelity sources like calibrated sensors. Another solution uses kriging to correlate data from sensors deployed at different locations. Other studies have explored and used EM based procedure or sampling techniques to train the model for solving the problem statement. Now, here I will discuss the author's ideas, that is, the proposed idea by the authors to solve the given problem statement. To give a proper context, I will start with the approach which authors come up with for solving the problem statement. Also, their approach converts the whole solution as a self monitoring system. From author's approach, simply filtering the faults can help clean the data, but uncovering the category of faults can be more important and helpful. Thus, they conclude that just having an understanding of the physical process which the sensor is interacting with is not enough. Rather, additional knowledge regarding the hardware status provides a context. Based on the context of hardware status, there are various types of fault associated with the different states of the hardware, namely short, noise, and constant. As these faults exhibit distinctive statistical patterns and provide important insight into further hardware failure diagnosis. Uncovering the categories of the faults may lead to informed decision making on remedy strategy. To tackle the problem, the author proposed a hybrid model that combines Bayesian dynamic linear models and hidden Markov models. The model is rich enough to capture the distinctive statistical patterns of the sensor faults, which are widely found in real world deployments. The proposed model and algorithm is coded and implemented in R. The solution given by the authors make multiple contributions. The model can infer both the physical process and also the sensor fault status at the same time. The model can automatically filter out the data faults without any ad hoc intervention. The efficient approximate online inference algorithm is derived for local processing. The one pass algorithm developed that requires no storage of training data. The solution achieves competitive inference results. Moving on to the differences that proposed solution has in comparison to existing solution. One of the key differences is the approach of the solution. While the currently existing solutions just rely on physical process that the sensor is interacting with, the proposed solution also takes into consideration the hardware status of the sensors to create an extra context for the learning model, facilitating the adaptive nature of the system. Additionally, the model can capture the distinctive statistical patterns of sensor faults which are widely found in real-world deployments, making it comprehensive. The specification of model is built upon the statistical properties of the faults but also can adapt itself to the data when required, minimizing the learning and modeling effort. In terms of evaluation, the solution has been coded in R and has been evaluated on synthetically generated data and real sensor data. The main reason behind two approaches towards the evaluation is that the synthetic analysis helps to empirically assess the accuracy of the inference algorithm, and on the other hand, the real sensor data analysis compares the solution with the baseline. As a result of the evaluation, it can be seen that HMS DLM automatically ignored the influence of erroneous observation without any human intervention. In my opinion, the paper has been written in a very well structured manner. All the sections are well placed. The paper is objectively focused and sticks to the main objective of the paper without delving into unnecessary details. Even though the paper gives a background section, the paper seems to assume that the reader has some sort of knowledge regarding the concepts being used. This makes the paper tough to read from the perspective of a general reader. Also, certain terminology makes the paper hard to understand for a layman. The paper also doesn't discuss the limitations and assumptions of the proposed solutions, which could be valuable information as that solution might not be applicable in all scenarios. In conclusion, I would like to say that the authors came up with a novel concept and tried to do justice to the same. The findings and the evaluations of the proposed solutions seem thorough, and also the inclusion of future improvements in the conclusion section makes it a good subject which can be further studied and explored. Thank you.